Standard electrode potentials. All right, so E naught. We'll be concerned with standard reduction potentials, right? So the voltage generated when a oxidizing agent takes electrons. All right, so for half reactions written as reductions, right? So electrons are the reactants, right? Something taking electrons. So what kind of voltage is generated when you're in your standard state? And when you're in your standard state, the substances are at 1 molar concentrations. So just as the overall cell of reaction can be thought of as the sum of two half cell reactions, the measured voltage of a cell can be treated as the sum of two electrical potentials, an oxidation potential and a reduction potential. All right, so it's impossible to measure something in isolation, right? So if something's being reduced, something's being oxidized. All right, so we had to have some sort of standard reference, and it was decided that the voltage generated when H plus ions took electrons to become hydrogen at 1 molar concentrations or 1 atmosphere pressure was going to be 0 volts. So the question is, are you a better oxidizing agent than H plus ion, therefore you'll have a positive voltage, and if you're a worse oxidizing agent than H plus ion, you'll have a negative voltage. If we add the oxidation potential, all right, the voltage generated when something is oxidized, to the reduction potential, the voltage generated when something is reduced, we get the voltage of the reaction, the voltage of the cell. All right, E sub cell. All right, the reaction. We've got hydrochloric acid, or, again, the chloride ions are spectated here. So H plus ion reacting with zinc to form zinc 2 plus and hydrogen gas. All right, so this is our cell diagram, right? Zinc is being oxidized at the anode, and H plus ions are taking electrons over at the cathode, and this is happening along a platinum surface. That's why you have platinum off on the right-hand side. All right, so the standard potential for this cell is 0.76 volts. So someone measures this, right? These are all measured voltage values. And since it was arbitrarily decided that the reduction potential for H plus ion was going to be 0, when you add the oxidation potential for zinc to the reduction potential for H plus ion, we get 76 volts. So that is the oxidation potential for zinc turning into zinc 2 plus. So oxidation potential. So if we want to turn this into a reduction potential, we just turn it around. All right, so if it's zinc turning into zinc 2 plus ion at a 1 molar concentration generates 0.76 volts. Turning it around, zinc 2 plus taking electrons becomes zinc would be negative 76 volts. So we live in a nice predictable universe, right? So if it's an oxidation potential going one way, it's the same magnitude of voltage going in reverse for a reduction potential. All right, if we recall, right, we had a cell where we had zinc losing electrons to copper 2, and it generated a voltage of 1.1 volts, and that was at standard conditions. So that means you've got a 1 molar concentration of the zinc 2 plus ion and a 1 molar concentration of the copper 2 plus ion concentration. All right, so since we know what the cell potential for this is, we can deduce what the reduction potential for copper 2 is going to be, now that we know what the reduction potential for zinc 2 plus is. So this is how you find reduction potentials for different oxidizing agents. So in this cell, it's copper 2 that is acting as the oxidizing agent, all right, that's being reduced, and it's zinc that's being oxidized. So we take the reduction potential for zinc 2 plus, we turn it around and turn it into an oxidation potential, and that means changing the sign, right? So zinc metal losing electrons becomes zinc 2 plus, generates positive 76 volts. Well, we know the overall voltage for the cell is 1.1 volts at standard conditions. So if I subtract 0.76 volts from 1.1 volts, I get the reduction potential for copper 2 plus, which is positive 0.34 volts. All right, so I guess what I'm going through with this step right here is showing where these reduction potentials come from. They're measured, All right, so if you know the oxidation potential for something and you know the voltage for the cell, you can find the reduction potential for the thing you're looking for. In this case, it was copper 2 plus. All right, standard reduction potentials. Why standard reduction potential? Well, I don't know. It was arbitrarily decided that when we make a table, we're going to look at how strong an oxidizing agent is, and we're going to compare them. So the more positive the voltage, the better the oxidizing agent. So here's a table, right? I copied this out of the book. That's why it's a little bit fuzzy. So up here at the top left-hand corner, we have fluorine. As we know, fluorine is a highly electronegative element. So when it takes electrons, it is it's a great oxidizing agent, right? It's able to take electrons. Don't mess around with fluorine gas. It'll kill you because it's going to take electrons. So it has a voltage of 2.87 volts. So this is a great oxidizing agent. And as we go down, the voltage gets less and less. So you could be becoming less and less of an oxidizing agent. So if I look at silver 2 plus, becoming silver plus, right, that generates a voltage of 1.99 volts. All right, that's just below it. So hey, silver mostly exists as a +1 oxidation state. So taking another electron off of silver, making silver 2 plus, well, that's going to be a very strong oxidizing agent. So and so on. So we go down the list. You can see hydrogen over on the right-hand side, right? So H plus ions taking 2 electrons become hydrogen gas has a 0 of reduction potential. So again, we're always compared to hydrogen. Are you a better oxidizing agent than hydrogen? That's the whole left-hand column, and then you go to the top with oxygen, taking electrons away from water to become hydroxide, and then you go down to hydrogen, and then you go below hydrogen, right? And now you've got negative values for reduction potential. So way down here in the corner, lithium is the best reducing agent, right? Turn lithium around, right? So it's lithium losing electrons to become lithium cation. That's going to have a positive 3.05 volts as a oxidation potential. So lithium is the best reducing agent. Fluorine is the best oxidizing agent on our chart here, right? So this is a kind of a truncated chart. Strongest oxidizers will be the most positive. The strongest reducers will be the most negative reduction as far as reduction potential goes. So lithium, the easiest to take electrons off of. Fluorine, the one that releases the most or generates the most voltage when it takes electrons. So as far as our reaction goes, right, copper 2 will take electrons away from zinc to form zinc 2 plus. All right, so this is where we get the voltages from, right? The reduction potential for copper 2 is 0.34 volts. If I turn the reduction potential for zinc 2 plus around, I get the oxidation potential for zinc. Right, so an analogy, right? When we were doing acid-base chemistry, equilibrium lie to the side of the weaker acid, right? So you're going to have a spontaneous reaction, a big K value, when you have the weaker acid over on the product side. So it's the same thing with oxidation reduction reactions. Identify the oxidizing agent, equilibrium will lie to the side of the weaker oxidizing agent. Oops. Lie to the side of the weaker oxidizing agent. So you have a big K value, spontaneous reaction. Positive voltage for the cell. So can zinc 2 plus oxidize tin under standard conditions? Well, we can answer this question by going to the chart. So we look to see where zinc is. There's zinc 2 plus and there's tin. So since tin 2 plus is a stronger oxidizing agent than zinc 2 plus, no. As far as the way the reaction's written, no, it will not zinc 2 plus will not spontaneously take electrons away from tin to form tin 2 plus. So when I look at the two half reactions, right, this would be the oxidation potential for zinc 2 plus. This is the oxidation. This is the reduction potential for zinc 2 plus. And this is the reduction potential for tin 2 plus, right? We looked them up on the chart. So if I want the oxidation potential for tin, I turn it around, and I would get the voltage for the cell. So no, zinc 2 plus will not take electrons away from tin in a spontaneous way. So what's the voltage for the cell? Turn like I said, turn the reduction potential for tin around, make it an oxidation potential, add it to the reduction potential for zinc 2 plus, and we get the voltage for the cell. So we get a negative voltage. A negative voltage for the cell implies a non-spontaneous reaction. So at standard conditions, when you have a negative voltage for the cell, this implies a small k value. So what is the standard voltage for the galvanic cell made between cadmium, right, in a 1 molar concentration of cadmium 2 plus, and a chromium in a 1 molar solution of chromium 3 nitrate? So here are the two reduction potentials, all right? So cadmium taking electrons, chromium taking electrons. When I look them up on the chart, yes, cadmium is a better oxidizing agent than chromium, so this will be a spontaneous reaction. Cadmium will take electrons away from chromium. So if I want to figure out what the oxidation potential is for chromium, I turn it around and change the sign. So when I add these two potentials together, the reduction potential for cadmium 2 plus and the oxidation potential for chromium, I get a positive voltage. So this means, yeah, it'll occur in a spontaneous way. Voltage is an intensive property, meaning if I balance this thing where I'm making 3 moles of cadmium metal and 2 moles of chromium 3 plus, it doesn't affect the voltage. So the coefficients don't affect what the voltage is going to be. So the electrons will flow. We'll burn up our chromium anode, and we'll decrease the concentration of cadmium 2 plus over at the cathode.